Greetings, I'm Ben, and in this video I'm going to show you a couple of tools in R to check your regression functions, your regression assumptions. A quick note, I'm not going to explain what the assumptions of regression are or what the diagnostics are in any depth. This video just assumes you want to really quickly see how to do something in R that you learned was important elsewhere. Okay, so let's start by running just a basic regression model. So we will call it model 1. And here we're going to run a linear model to try to explain the feeling thermometer evaluation of Donald Trump using age, a dummy variable for male, a dummy variable for white race, party identification variable, an item that asks people what they think the government's role should be in combating income inequality, an item that asks people about their attitudes toward abortion, and the racial resentment scale used in political science frequently. And the data for this is the American National Election Studies pilot data from 2020. So we run that model. Whoops, that would be data equals, not data plus. Okay, then we can get our summary of that model, model 1. So you can see our coefficients, our p-values, the output that you typically see. We can also get our standardized regression coefficients with the LM beta function from the quant psych package. But one thing that we may be interested in doing is checking for multicollinearity. And so the way that people most often check for multicollinearity is by looking at the variable inflation factor, or the VIF, and you can do that with the car package. So you can install car. I already have it installed here, so I'm not going to do that again. And then load it. And again, I already have car loaded, so I'm not going to load it. But once you have that, you just type VIF for this is the function that you want in the car package. And then you put your model name here. So I named it model 1. So I type that there. And it gives me the VIF for all of the variables in the model. And notice all of these are lower than 10. They're also lower than 5. So most people would be pretty comfortable that we don't have an issue of multicollinearity in this model. Okay, now you also might want to inspect the residuals of your model to see if they're normally distributed. And the base stats function, or the base stats package in R, has a resid function that'll allow you to output the residuals. And so I will do that now by typing resid.model1 and then resid model1. So what is this syntax? This is the object that I am outputting my residuals to. I created that name arbitrarily. You can make whatever name you want. This is my little arrow. Resid is the command that says I want you to take a model, a regression model, and output all of the residuals. And then this is the name of the model that I gave it up here. And so that's what I want to put in the parentheses. So I've done that. Now I've created a new data frame that's just the residuals from my model 1. And so I can get a histogram of that data frame. And the syntax for this is just HIST to get a histogram. And then this is the object that I created up here. So if you named your residual output something different, you would put something different here. So you can see here we have the histogram of our residuals. We can, make it a little bit taller if we would like. And say like, oh, okay, those look pretty normally distributed. Now, you also might want to get a residuals plot, and there's actually a cool package to do that called ggforitfy that leverages ggplot. So you'd want to go install packages ggplot 2 if you don't have that installed. I already do. And then library ggplot2. And if you run these 2 lines, it'll install and load ggplot2, install packages ggforitfy, and library ggforitfy. Run those 2 lines of code and you'll install that package. And then here you just type autoplot and then the name of your model. So again, I named it model 1, and so that's what I'm going to use. But if you named your model something else, use the name of your model here. And then which, and this says there are a series of plots that you can ask for. So you can ask for 1 through 6, and that'll give you 6 very common diagnostic plots used in regression. Or you can just say which equals 1, and it'll give you the first one. Or I'm going to say which 1 and 2. And in R, if you haven't seen this before, anytime you want to make a list of things, so here I'm making a list of the first diagnostic plot and the second diagnostic plot. So when you list in R, you always use C parentheses to do so. And then you can say, all right, label.size equals 3. And I don't know, you can play around with whatever you want the label size to be. So I selected 3. I don't. All right, so if we run that, you'll see it gives us the residuals versus fitted, which is the first plot. So that's when we put that I want 1 after the which command. It's going to give us the residuals versus fitted. And then the second is that normal QQ plot. And so these are the 2 plots you get by saying I want plot 1 and 2. Let's do this again, but get some different ones. So let's do that again with, let me make this just a little bit so you can see the closed parenthesis there and everything. Let's get 3 and 4. So see, this gives you a scale location plot and Cook's distance. And then finally we can do 5 and 6. And this gives us residuals versus leverage and Cook's distance versus leverage. So you see we can get a variety of different diagnostic plots from the ggforitfy package using ggplot2. So very handy. Now, what if we want to test for homoscedasticity or heteroscedasticity? To do that, we can do the Bruch-Pagan test. Using CAR, CAR calls it the NCV test. And so we would do NCV test is the name of the function. And if you haven't installed and loaded CAR, then you need to do that to get the function NCV test. And then again, this is just the name of the model that we ran. And so we run that and you see we actually don't have, we fail the test, you would say. We have heteroscedasticity, or we violate the assumption of homoscedasticity. And so what do you do when you violate the assumption of homoscedasticity? Well, one thing you can do is correct your standard errors and see if your coefficients generate the same substantive result on the hypothesis test after correcting your standard errors. So to do that, you're going to need 2 more packages. So we'll go install packages. The first one is lmtest and library lmtest. Again, I already have that installed and loaded, so I am just illustrating to you that this is something you could type to get the lmtest package and the sandwich package. So we will use the lmtest and sandwich package for the following functions. You can do, so the lmtest package has a coef test, which will run a coefficient test using corrected standard errors. And so we'll do a coef test on model 1, and then to get the corrected standard errors, you need to use the vcov.hc function from sandwich. And again, you need to tell it what model do you want to correct the standard errors. Model 1. So here, this is the function from lmtest. This is our model name. This is the function Well, this is the function from sandwich, and again, our model name, and this will give us the tests of our coefficients with corrected standard errors. I'm going to make that a little bit wider so that it's all on a line. Well, it's still not all on a line. Let's try that again. There we go. And so now you'll see the standard errors have been corrected for heteroscedasticity, which means that our p-values or our null hypothesis test will be robust to violations of the assumption of homoscedasticity. So those are the most common procedures that people like to do to test the assumptions of their regression model. Hopefully you found this quick and helpful. You might want more explanations about some of these assumptions, or more explanations about what these violations mean or how to interpret these plots. This video, I just wanted to show you how to do those things. There are a lot of wonderful resources online, lots of other great YouTube channels that dive into depth on these assumptions or on how to interpret the different plots that you get. Hopefully you found this a quick, easy, very digestible explanation of just how to do the tests. Thanks for watching.